Hi everyone, so I'm Victoria and today I'll be talking about multimodal learning. So first off, I'm going to talk about what multimodal learning is and what are the challenges associated with it. And then I'm going to talk through some examples of how we can apply multimodal learning. So first I'm going to talk about a Flickr example where we're tagging images, and then I'm going to talk about image captioning where we're generating sentence descriptions of images. And then I'm going to talk about SoundNet, which is learning sound representation from unlabeled videos. So first off, what is multimodal learning? A modality is just sort of a kind of data. So we've seen a lot of success with looking at images, such as classifying digits from MNIST. And we've seen speech recognition, looking at audio waveforms. And we've also seen text in our sequence modeling lecture. But multimodal learning is just learning that involves multiple modalities. And this can manifest itself in different ways. So it could be a model where the input is one modality and we're trying to translate it to a different modality. Or it could be that we're learning two modalities both as inputs to the model. Or it could be something like one modality we've already learned and we're trying to use that to assist in the learning of a new modality. And there's lots and lots of different ways, but these are just some examples of how we can use multiple modalities together. So just to motivate this, most of the data we see in our daily lives is in multiple modalities at the same time. So for example, on Facebook, you might see a post that has a text description, an image, as well as likes or comments. On Flickr, you might have an image that also has tags or a caption. You might have a product recommendation system like Netflix, where you've got the audio and video of the actual TV show, but you might also have really useful information in the description or in the user comments and ratings. And also, this is really interesting in robotics, where we almost always have multiple modalities. So for example, if you have a self-driving car, although you probably don't actually have one, you might have LiDAR, camera, audio, and other sensors that are all combined to build this model of the world. So why haven't we done a whole lot of multimodal learning? You know, it sounds so great. Well, these different modalities have very different representations. So if you think about images, these are real valued and really dense in the form of pixels, compared to something like text, which is very sparse in comparison and discrete as well. So it's really hard to combine these two different representations into one model. In addition, if you think about different data sets that are combined into different modalities, they might be very noisy, such as in this cat picture, we've got a lot of tags that are about the camera that was used to take the picture, which isn't going to be that useful for our computer vision application. Similarly, only 30% of users in this Flickr example have tagged their photos. So there could be a lot of missing data as well. So there are some things that we can do in general to get around these problems and solve multimodal learning problems. So the first general thing we want to do is we want to combine separate models that are on single modalities at a higher, more abstract level. And this allows us to pre-train different parts of the model on single modality data, which we might have in a lot more abundance. For example, we might have tons of images, but only some of them are tagged. And the way we're going to combine these is using embeddings, which I'll explain a little bit. So first off, pre-training is simply initializing the weights from another network that we've trained previously. So normally when you're training a neural network, you might initialize them randomly with sampling from a Gaussian or something. But we can pre-train it and use, say, for example, if we have a network we've trained on ImageNet classification, it's going to learn a lot of useful features about images. As you can see here, this is the first 5 conv layers from an ImageNet network. And it's learned a lot of these edge filters and color filters that we've talked about previously. And then all the way up to layer 5, where it's learning higher level visual stimuli, such as different objects or circles and corners and things like that. So even though the task isn't the same, we can reuse a lot of these weights. for different vision tasks, even if it's not exactly the same as ImageNet. And next up, embeddings are just a way to represent data. And in deep learning, what we usually mean by this is a high-dimensional space where each piece of data is a vector. So we could use a neural network to train an embedding where we're converting a piece of data into this high-dimensional space. But we can also use a neural network to take an embedding vector as an input. And so we can use this to sort of convert between modalities. And to make that a little bit more clear, here's an example that you might have seen of word embedding. So you can imagine a high-dimensional space where each word is represented by a high-dimensional vector. And so there are some really interesting properties of these. You might have seen this example where we can learn analogies in this space. So if you have the vector representation for king, and the vector representation for man, and the vector representation for woman, you can solve the analogy king is to man as queen is to woman by taking the king vector, subtracting man, adding woman, and you get something pretty close to queen. You can also do this for verb tenses, such as walking goes to walked, swimming goes to swam, and you can even do geography in this space. And you can take countries and go to capitals, and I think sometimes you can even go like, find me something east of Germany, and it's all sort of preserved in this high-dimensional space. Question?
Can you make a comment on what the dimensions actually are?
So it depends on what task you're trying to solve, but maybe you have a 500-dimensional space or something like that. Yeah?
Yeah, so how do you train word embedding models?
That's not super relevant to this lecture, but you can imagine one way you could do it is a skipgram model where you have, you basically try to predict a word given its contextual words. And that sort of builds up this space where you know words and words that are associated with them, and you can sort of learn the space that way, if that makes sense.
I have a second part of the question. So how do you know that like the different components of like the vector that represent the word are like semantically meaningful for humans as opposed to machines?
Yeah, so the actual dimensions in this embedding might not mean a whole lot because they're all being learned sort of naturally. But yeah, you can sort of see that they're semantically meaningful through these examples by subtracting vectors and things like that, or even just looking at words that are near a high-dimensional vector. So, near king, you might have other types of royalty like duke or prince and things like that. You can sort of observe these by looking at these word embeddings. So in general, we can use embeddings to switch between modalities. So if you remember in the sequence modeling lecture, we were looking at a sentence embedding for a translation model. So we had one model that would take in an English sentence and create this state or sentence embedding, which was fed into another model, which takes the sentence embedding and spits out a French sentence. But we can also use this to convert between different modalities. So we can have embeddings for images or for audio or for any modality. And we can use this to convert at a higher level of meaning. So next up, I'm going to talk about the Flickr example where we're joint learning images and tags. So in this task, we have images and we have tags. And in this data set, there are 1 million images, but only 25,000 of them are really well labeled. And so our goal here is to create a joint representation of images and text, which might be useful, say, if someone's searching Flickr for photos of sunset, you want to find all of the sunset photos, not just the users that took the time to type sunset next to their little image. So we're going to use this idea of combining unimodal models at a higher level. So I don't want to go a whole lot into the details of this particular model, which is a deep Boltzmann machine, which is a little bit different from a neural network. But you can just imagine we have an image-specific model and a text-specific model, and then we have this joint representation at the top, which sort of combines the two models. And so we input the image to the image-specific model and the text as word vectors into the language model. And so the task here is to try to build a joint embedding space. So this embedding space has both images and text in it, which is sort of interesting to think about. But basically, you'd want the word vector representation of sunset to be close to the image vector representation of this picture. So we can look at some examples of this model. And given, say, this picture of a cat, the vector for that is close to the words dog, cat, pet, kitten, tongue, furry. So it's working pretty well as an automated tagger for Flickr. It doesn't always work that well, though. So here are some sillier examples. So for example, in this second image, we've got some sort of bird, and it's all about politics and Obama and hope and change. And you might imagine if this model doesn't have any semantic notion of a bird, this looks a lot like one of those Obama posters with the blue and the white.
Is that the lame duck?
Yeah, so the takeaway here is that it's really important what you're pre-training on. So this, the image network here was not pre-trained on a data set that had a lot of animals in it. So it didn't really have any idea what an animal was. And so if you squint really hard and you don't know what a bird is, I could see Obama in that picture. So yeah, just remember that the task that you're pre-training on, it should be sort of related to the task that you're trying to solve, or there might be problems there. And we can also go the opposite direction. So given some tags from Flickr, can we find images? So the cool thing here is that this is actually a really simple problem once we've built our joint space, right? It's just a sort of a nearest neighbors problem where we take the vectors for water, red, and sunset and try to find images near those. So it's doing a pretty good job of finding images of sunsets over the ocean that really match our labels. Here's something really cool you can do with this joint space, is you can do multimodal arithmetic. So let's say you have this image of the Taj Mahal. You take its vector representation in this high-dimensional space. Then you subtract the vector representation of day, and you add the vector representation of night. Then you might actually get pictures like this, where it's buildings at night that sort of look like this picture. So that's pretty cool. You can even do, kitten in a box, and you want to change it to pictures of kittens in bowls. So, except for, the mouse and the duck. So next up, I'm going to talk about image captioning. So image captioning is the task where you have an image and you want to generate an entire sentence for this image. So it's a little bit different from the Flickr task where we just had these tags. Now we actually want to build a coherent sentence describing this image. And so this paper, Show and Tell, came out in 2014. And they had this great simple model where basically they just took the CNN part, which we already know works really well on images, and you build up this image embedding, and then you feed the image embedding into an RNN, which we already know works really well for generating language. So let's take a closer look at this model. So we're feeding an image into, here they're using an Inception CNN. But basically the CNN, which you can pre-train, is creating an image embedding. And then we're using this image embedding in the same way that we used the translate model, and we're feeding it into, as a high-dimensional vector, into a language model, which can then produce a caption using the information stored in the vector we gave it. So here we see we've got sort of, again, this separation of different modalities that are combined at a higher level. So now let's look at some examples of how this works. So here we have an image which is fed into the model. And we've also got a human that has labeled this image with a caption. The human says, "A young girl asleep on the sofa cuddling a stuffed bear." And the computer has generated two captions, which is sort of cool. You can sample the space and get different captions for the same image. And the computer says, "A close-up of a child holding a stuffed animal, and a baby is asleep next to a teddy bear." So this is really impressive because not only has this caption generator learn the different objects in the image, like the stuffed animal and the baby, but it's able to sort of learn the relation between them. You know, the child's holding the stuffed animal. So that's pretty impressive, I think. Here's some other examples. They don't all work super well, so here you see it's a bottle of wine and not bottles of beer, I guess. Here you've got a cat in a car. Maybe the cat was supposed to be black, not the car, but you know, it's getting some idea of this image. Sometimes it doesn't work that well. So this image, the computer says, a man flying through the air while riding a snowboard. So you can see we've still got some improvement to make, but sometimes they make funny pictures with funny captions. There's this other cool thing that Jamie Kuros from University of Toronto has done with this caption model, where instead of having the captioning part of the language model, she replaced it with a language model that was trained on romance novels. We can get sort of this romantic novel paragraph about this image. So it says, you know, the sun had risen from the ocean, making her feel more alive than normal. The sun was just starting to fade away, leaving people scattered around the Atlantic Ocean. So the paragraph doesn't make a whole lot of sense as a whole, but it's really exciting that we're able to combine these very different modalities in interesting ways. And we're still sort of getting some of the information in this image. So there's lots of ways you can combine these models. So next up, I want to talk about SoundNet. So in this example, we want to learn a representation for sound, for audio, which a lot of people haven't focused that much on outside of speech recognition, say. And so the way we're going to do this is we're going to use unlabeled videos. So they're unlabeled, but they have this great synchronization between what you're seeing and what you're hearing. So, you know, if I hit this table, you saw it and you heard it, and there was this great timing sync up, you know. So we can use this information in these two modalities to learn about sound. So what we're going to do here is we're going to look at these unlabeled videos, and we're going to use these vision models that we already know are really good, and we're going to use these vision models to help us learn about sound. So here's the model that's used. We've got unlabeled video, which we split up into RGB frames and the raw audio. The RGB frames are fed into already trained vision networks. So we've got one network that's trained on ImageNet, which we've seen, which learns object information such as there's a zebra in the video, or you know, it's got lots of birds. And then we're also feeding it into this Places CNN, which if you remember is a data set that has information about scenes. So it could have, this is a beach, or this is a park, things like that. So we can use these vision networks as labels for the video. So we get object and scene information basically for free, which is really cool. And so we can use this object and scene information as a label for our sound. So for example, if you've got a video of birds, they're probably chirping. And so we can learn this sort of natural way, we can naturally learn that birds chirp, and this is what birds look like, so we can associate those two. So how does this work? We have a raw waveform that's just it's being fed into a one-dimensional convolutional neural network with many layers. And this is outputting sort of a high-dimensional vector, like a sound embedding. And we're basically just trying to minimize the distance between the object and scene information and the audio embedding. And so we're going to use KL divergence for this, if you've seen that. So if you imagine X is the raw waveform, Y is the frames, G of Y would be the object or scene information as retrieved from these vision networks, and F of X and theta is the output from the sound CNN given the parameters that we're training on. And KL divergence, if you're not familiar with it, it's sort of the difference between two probability distributions, which are discrete here. So you can say like, oh, there's a probability of 0.1 that there's a zebra in this video. And we want to train the sound net to also predict 0.1. So basically, it's just a sum over the different classes. and we're doing probability from one distribution times the log of the fraction of those probabilities. So once we've trained this network, we can do some really cool visualizations. Or I guess it's not really visual because it's audio. But basically, you can imagine focusing in on one neuron. So let's say we've got this neuron in COM7, the last hidden layer. And we're going to keep track of when this neuron is getting activated. So just when it's outputting a high number. And we can keep track of which audio activate it the most. So if we feed in our entire data set, we can say, hey, here are the top 9 sounds that activate this neuron. So this is really interesting because we expect the neural network to learn hierarchical representation of whatever task we're training on. So if we're looking at audio here, we expect COM7 to have some high-level features about audio. So I've got a little visualization here. So again here, so these are each representing one neuron in this network in COM7, the last hidden layer. And we expect them to learn these high-level representations of sound. But remember, these are all sort of unlabeled. They only have words here because the author of this paper has gone in and said, oh, hey, these sound like motors, these sound like dogs. And the images, again, so if you have some like barking audio that's really stimulating a neuron, then you can find the frames associated with it. So that's how this visualization was made. But remember, the frames are not actually going into the sound net. So we can listen to some of these. Let's see if this works. So remember, these are not generated sounds. These are just the inputs that maximize some neuron. But it's really cool, these high-level representations of sound that this network has learned. So here we've got underwater. This one's sort of funny. This is, most of them seem to have babies in them, but it's parents talking to babies.
The topic's not the last, eh?
In Granddad's house. Coming over.
You are? Hi.
So these are sort of fun to play with. We can also look at other neurons in other layers. So we expect CON7 to have higher level features, but we can look at CON5, say, which will learn lower level ideas about sound. So here we've got a laughing neuron in CON5.
210 colors.
So these are really cool because this is all done sort of naturally with this vision, supervision idea. We've got music. So these are really exciting, I think. We can also look at the visualizations from the first level of neurons, but these aren't super meaningful to humans because it's very low level. So they're sort of just different tones, but again, this is from a 1D convolutional network, so you can actually visualize what the waveforms look like. Okay. So enough about SoundNet. So in conclusion, we've seen that multimodal tasks can be very difficult because there's all these differences in how you represent data, and there can also be noisy or missing data in these multimodal data sets. But we've also learned how we can overcome these difficulties through the composition of many separate models at a higher level, and we can also pre-train in unimodal cases, especially with images. This is really useful. And we've seen 3 examples of these multimodal tasks. We've seen how we can model 2 modalities jointly with flicker tagging. We've seen how we can generate one modality given another. In the case of given an image, can we generate a sentence caption for it? And we've also seen how we can use one modality to get a better representation of another modality, like we've seen in SoundNet. And so here I just want to say, if you need any project ideas, think of 2 interesting modalities that you might find together, and think about projects you could do there. There's so many different modalities out there, and I'm sure you can find 2 modalities that have not been learned together before. So now I have time for questions. Yeah?
So in speech recognition, they normally feed in like spectrogram-related features. Why did SoundNet choose to feed in the raw waveform? Is there any particular reason?
I think it's usually more impressive when you can take the raw data and learn basically end-to-end. And I also have seen recently some speech recognition systems are also doing end-to-end learning. Yeah. Any other questions?